Okay, let's take a look at question 9 in sample exam 3 for Chem 11. This is a question about work function and the photoelectric effect concept that we also learned before. This one says we have a work function of a metal, cadmium in this case, and it has a value of 392.99 kilojoules per mole. And the question is which of these lights can actually ionize the electron in the cadmium metal. So just a reminder real quickly of the photoelectric effect experiment. You have a metal that has a bunch of electrons on them, and you shine light on the surface of the metal, and this light has to have a certain frequency, which we call nu naught, or the threshold frequency. And as long as that light has that threshold frequency or higher, then the energy from the light can be enough to knock out one of these electrons off from the metal, and that's what we call ionization, right? So at the minimum, then the energy to ionize the electron must equal the energy coming from the light that's being shine on the surface of the metal, okay? And we call that minimum energy, right? The energy needed to ionize, we call the work function, and it has that symbol, phi, okay? And so basically phi is just h times nu naught, right? H, Planck's constant, times the minimum frequency or the threshold frequency needed to ionize. So basically here what we have to do is first figure out what our value of phi is, the work function, for each electron, and then afterwards we can then figure out the wavelength that would allow us to ionize the electron. So we start with the value of the work function being 392.99 kilojoules per mole. But if you look at the drawing that I just had in here, the interaction that's illustrated here is between one photon with one electron. So what you need to do is convert the value of the work function that you have to one electron instead of for 1 mole of electron. And to do that, you're going to need your Avogadro's number. So 1 mole of electron is the same as 6.02 times 10 to the 23rd electron. And then we can convert the kilojoules to joules, since we're going to get a real small number here. And if you do that, you should get 6.53 times 10 to the minus 19 joules. Now, once you get that, this is per electron, we can say that the minimum energy of light that's needed, so energy of the photon, must equal to the work function, right, in order to be able to knock out the electron. This is at minimum. So that should equal to, since energy of the photon is equal to hc over lambda, we can say that hc over lambda is equal to work function. We're looking for lambda in this case, so lambda is going to be equal to hc over phi. Now the lambda here is going to be lambda maximum, because if frequency is inversely proportional to wavelength, right, nu is equal to c over lambda. So when we're talking about a threshold frequency or a minimum frequency, that's the same as talking about a maximum lambda, because they're inversely related to each other. So to solve for lambda maximum, I need to plug in my Planck's constant, and then my speed of light, and then my phi, which is 6.53 times 10 to the minus 19 joules. And then what I get is a value here of lambda maximum of 304 nanometers, okay? So it's 3.04 times 10 to the minus 7 meter, and I'm just converting that directly to nanometer because that's typically the value or the unit that we would use for these type of light. And so what you have to do then is you say this is your lambda max. In other words, your light can't be any longer than this wavelength. So if we look at the options that we're given in terms of the light, UV is shorter than that, so that's good, right? Because that's lambda max. That's the highest value you can have, is 304. The next one is already blue, and blue is 400 nanometers, so that means that wouldn't work anymore. And the rest of them is all higher than that. So the only one that would work is then UV, which is C.